Hello again, it's me, Professor Albert, coming again with Lesson 6. Let's learn some economics. So today our goal is to talk about the different utility functions, namely complement, substitutes, Cobbs-Douglas, and quasi-linear, and map between their functional form and the actual graphs that we've been working with. We're also going to figure out how to find the marginal utilities given these functions, find the marginal rate of transformation as well as marginal rate of substitution, and finally set up the utility maximization problems that we've been working towards all along. So first let's start off with the usual suspects, as I call them, the different functional forms we'll use all the time. The first one looks like this. Let our utility be a function of q1 and q2 such that it equals some number, call it a, times q1 plus some number, call it b, times q2. First off, how would we draw indifference curves for this function? That is, fix your utility, let utility equal 1 for starters. How would we vary q1 and q2 in order to maintain a constant utility? Spend a moment on your own and figure out what these utility curves would look like. So if I were to try to draw this, I'd first say let's zero out one of the units. So if I have one util and I have 0 q1, it seems like this must be 1 over b. 1 over b, if I have 1 q, that will give me b times q1 plus 0, i.e. 1 utility. Similarly, if I were to try to find how many q1 give me 1 util, I'd have 1 over a. The next question is, well, what do we do in between these 2 points? Well, if I had half of each, that is, if I had 1 over 2b and 1 over 2a, it would be somewhere about here. If you connect these 2 points, you'll find that you have a straight line. This is perfect substitutes that we've seen. You'll notice that we have straight downward sloping indifference curves parallel to each other with equal space. So anytime you see something of the form a times q1 plus b times q2, where a and b are any numbers, these linear utility functions give us these straight lines which are perfect substitutes. Let's do another one. Let's suppose for a minute that our utility is given as the min function of a times q1 and b times q2. That is, observe q1 and q2, find a times q1 and b times q2. The smaller of these two quantities, that's how many utilities we have. Again, take a minute and try to draw what this might look like. For starters, just set let utility equal 1. How many q1, how many q2 do we have? So, first off, let's do the easiest thing. How can we easily find a point that has 1 util? Well, if we have 1 of a times q1, that seemed to me like we'd be here at 1 over a. And similarly, we'd be here at 1 over b. The next question is, well, what happens to my utility if I increase my q2 alone? Well, note that I'm looking at min of 1 over a times a q1, which is 1. Then I have 1 over b times b. That equals min of 1, 1 equals 1. Now, you will note something interesting happens if you vary either q1's quantity or q2's quantity. I.e., let's try min of some arbitrarily large value of q1. Let's try a times 10 and keep 1 over b times b fixed. What is the min of 10a and 1, assuming that a is greater than 1? Well, it'd still just be 1. So you'll note as we increase our quantities of q1, we still stay on the utility equals 1 line. And the same can be said for if we increase our quantity of b. So in this way, we will trace out these big L shapes like we saw before with perfect complements. That is, we have these vertices, which give us the minimum quantity for any utility. And then if we increase in either direction alone, we stay at the same amount of utility we had before. So anytime you see a min function, i.e. a utility of the form min times some linear function of q1, comma, some linear function of q2, know that these are going to make big L's for you. It's just a matter of scaling them properly with the a and b coefficients. Now, I could go through the same exercise for our other two usual suspects, namely Cobbs-Douglas and quasi-linear, but these are a little harder to draw because we have exponents in our coefficients and these things get a little messy. So instead, I'll just tell you what to look for. Anytime you see smooth, curvy lines that don't cross your x or y axis, you're probably looking at Cobbs-Douglas or something similar. Cobbs-Douglas are given by anytime you have q1 and q2 multiplied times each other with coefficients. We'll call them 1 and 1 minus a. And you'll note that 1 and 1 minus a sum to 1, and each should be bound below by 0 and bound above by 1. The easiest thing to do would just have q1 to the half and q2 to the half. But you also could have q1 to the third and q2 to the 2/3 or any other permutation. Anytime you have some function that looks like q1 and q2 multiplied times each other with coefficients that add to 1, you're looking at Cobbs-Douglas. And in the graph again, you're going to have parallel curvy lines that are smooth throughout and don't cross your axes. Quasi-linear looks a little like this. Quasi-linear is anytime you have some sort of concave function, we'll just call it function of q1, plus q2 linearly. This could be log of q1, this could be square root of q1. Anytime, again, you have a coefficient q2 added to some concave function of q1, that'll be quasi-linear. And as far as our graph goes, quasi-linear looks kind of similar to Cobbs-Douglas in that you have smooth, curvy, parallel, sloped, curvy bits. However, these will intersect either your y or your x-axis. So the first thing we're going to need to do before we start working on maximizations is work on finding marginal utilities. So here I've listed the 4 main functional forms. Spend a moment for each finding the marginal utilities. The marginal utility for each I will define as taking the derivative of utility with respect to the relevant q. So for each of these, first off, just find the marginal utility with respect to q1. I.e. take du dq1 for each of these. You also will want to find the marginal utilities with respect to good 2, because we'll need those in a minute too. All right, so first off, if we take du dq1, you'll note that bq2 dq1 is 0, right? There's no q1 terms here, those go away. If I take daq1 dq1, that's just going to be a. Similarly, for q2, we would just have b. Perfect complements. So when you try to take derivatives here, you're going to run into a bit of trouble. Why? Well, because the min function isn't differentiable everywhere. So I'll just tell you that when you draw these lines, the marginal utilities depend on where you are. That is, if you're on this part, do we have too much q1 or too much q2 if we're trying to consume optimally? We're trying to consume as cheaply as possible while staying at this fixed utility level. Well, it seems like we have too much q1, right? We're to the right of the axis. So our marginal utility with respect to q1 at any point to the right of this dot is just going to be 0. Similarly, if we're anywhere on the vertical section, we have too much q2 with respect to our q1. So therefore, our marginal utility will just be 0. So for perfect complements, your du dq1 will be 0 if you have more aq1 than you have bq2, and vice versa if your bq2 is higher than your aq1. The other marginal utility will just be the amount by which you're catching up. That is, if you are, say, here, well, we have too much q2 relative to our q1, so any amount we move to this way will increase our utility by a, because our q1s are scaled up by a. Cobbs-Douglas, we can just do some typical calculus. Here, all you got to do is take the proper partial derivative, and I'll tell you if you did it correctly, you'll have a times the utility of q1 and q2 divided by q1. Quasi-linear, you can do similar tricks. You're just going to find whatever the first derivative of this function is, that's your marginal utility with respect to good 1, and your marginal utility with respect to good 2 is just going to be 1. The next thing we should do is define the marginal rate of substitution, which we will call the MRS. The MRS is the rate at which a person would be glad to trade some units of good 1 for some units of good 2. The reason we'll do this is because if they trade at this ratio, they'll maintain the same level of utility. So imagine you've got some apples, you've got some oranges. There's some ratio at which you'd willingly exchange these, you don't care. That is your MRS. In order to find your MRS, assuming it's differentiable, all you're going to want to do is find the marginal utility of with respect to Q1 and place that over your marginal utility with respect to Q2, and we'll make it negative because this is downward sloping. That is, at any point on this, the slope of a line tangent to this curve is just going to be negative marginal utility with respect to good 1 divided by negative marginal utility with respect to good 2. And we will, for shortness, call your MU1 just big U1 and MU2 just big U2. And that'll give you the slope of this curve at any point. With that in mind, spend a minute, find the MRSs of each of our 4 usual suspects. All you have to do is divide your marginal utilities. Put negative MU1 divided by MU2. So the first one's pretty easy. We saw that perfect substitutes, MU1 was just A and MU2 was just B. So all we need is negative A over B. And that makes sense, right? For perfect substitutes, we're going to have lines like this. The slope of this line is just going to be negative A over B. So at any point along this line, that will be your slope. Your MRS for perfect complements will be a little trickier. We said before that your marginal utilities will either be A or B if you're deficient in Q1 or Q2 respectively, or 0 if you already have enough of that good. So anytime we're looking for an MRS, we're either going to be here, here, or here. If we are here, our marginal utility with respect to good 2 is 0. So when we look at negative U1 over negative U2, we're going to have division by 0. That means our marginal utility with respect to good 2 here will make our MRS tend towards infinity. Similarly, if we're over here, our marginal utility with respect to good 1 is 0. So we're going to have 0 over B, which is 0. And if you're at the vertex, well, at that point, you get 0 marginal utility for both. Your MRS there is not going to be defined. It's not a good place to be. Next, for Cobbs-Douglas, here you just apply your calculus tools. Bring your alphas down, take correct partial derivatives. All you're going to find is that you get negative A divided by 1 minus A times Q1 over Q2. You'll note that these are curvy and that this Q1 over Q2 changes as you move along the curve. So you're not going to have a constant marginal rate of substitution, right? Because these slopes are not constant. Quasi-linear, you're just going to have the derivative of whatever this function was divided by the derivative of this, i.e. you're just going to have du dq1 plus divided by 1. The next thing we're going to need is the marginal rate of transformation. This is the rate at which the market will allow you to exchange goods 1 for good 2, i.e. it's going to be points along a line that allow you to trade maintaining the same value, i.e. staying at your budget. The budget line is going to be the maximum quantities of Q2 and Q1 affordable. So what's the function of this line again? How did we get this? Well, you might remember that we defined your budget line as y equals Q1 P1 plus Q2 P2. Next, we're going to want to find the slope of this line at any given point. That is, along this line, pick a point, how do we find that slope? Hint, what did we just do to find the slope of our difference curve so we could find MRS? Well, note, we could just take the derivative of y with respect to q1 and divide that by the slope, by the derivative of y with respect to q2. If you do that, you'll note that dy dq1 is p1, and dy dp2 is q2 is p2. So we're going to find the slope of this line is just the ratio of the prices, that is negative p1 over p2. Now, the reason we need these is because these will be the fundamental tools we apply in order to solve the consumer's maximization problem. So let's properly define the consumer's maximization problem. Imagine that your consumers are trying to maximize their utility function subject to some budget. This transparently refers to some sort of constrained optimization problem, right? We have our utility, which is a function of Q1 and Q2, and we want to maximize this function as long as our Y, i.e. the amount of money we have to spend, is at least as big as the addition of Q1 P1 plus Q2 P2. My next question for you, you guys have all had calculus, how do I solve this? Can we solve this as written? Well, you might note, as written, this has an inequality constraint that says I've described this as y must be greater than or equal to p1 q1 plus p2 q2. In fact, solving this as written is a little complicated because I have to check not just all points along the budget line, but also all points not along the budget line. Could be here, could be here, could be here, could be here, could be here. There is one thing we've assumed that tells me the optimal ratio of Q1 and Q2 are going to be along this line. What rationality assumption told us that we are likely to be consuming along this line? Well, you might remember we also assumed non-satiety, i.e. more is better. So we are assuming that we, at all times, would like to have more of either Q1 or Q2. That is, we know we don't want to optimize here if we have Y dollars to spend, because there's these points out here which must, by assumption, give us more utility. Therefore, are we actually maximizing our utility subject to y being greater than or equal to q1 p1 plus p2 q2? No. We could actually just assume that these are equal, right? At any point, we are spending less than our budget. There's some also affordable bundle, slightly to the north and east, that will give us, we know, higher utility because we're non-satiated. Importantly, if we are to actually solve this problem, this we'll do in a later lesson, we're going to find, as we showed graphically, we want the point at which our budget is tangent to the highest indifference curve. You'll note we just saw that the MRT gives us the slope of our budget, and our MRS gives us our slope of our indifference curve. So in fact, when we're trying to maximize this problem, we're just trying to find a point such that our MRS equals our MRT. So although we'll go through the full Lagrange procedure next time, you'll always note that if you do it correctly, your interior solutions, that is your solutions where you're spending a little bit on each good, are going to be defined by this point where MRS equals MRT and your budget is obeyed. That's all we have time for this time.